The European Space Agency's PLATO mission is a space telescope designed to search for habitable planets outside of our solar system. The telescope will observe over 200,000 stars over 4 years, with the hope of finding Earth-like planets in the habitable zone that may be home to alien life or could sustain human life in the future. The habitable zone, often called the Goldilocks zone, is a specific region around a star where the temperature is just right for liquid water to exist on a planet's surface. Liquid water is so important because it is the key ingredient for life to begin anywhere in the universe. PLATO stands for Planetary Transits and Oscillations of Stars. It is a telescope designed to detect and characterize a large number of exoplanetary systems, including terrestrial exoplanets orbiting bright solar-type stars in their habitable zone. PLATO will provide data on planetary radii and architectures using the photometric transit method. The photometric transit method is a technique used to detect exoplanets by measuring the periodic slight dimming of a star's light as a planet passes in front of it. By analyzing the light curve, a graph of brightness over time, scientists can determine a planet's radius, orbit, and atmospheric composition. The light curve data will also enable information to be obtained on the star via astroseismic analysis. Data analysis from the PLATO mission will be combined with high-precision spectroscopic ground-based follow-up observations, enabling accurate planetary masses and mean planetary densities to be determined. The overall scientific objectives that PLATO will investigate are: how do planets and planetary systems form and evolve? Is our solar system special, or are there other systems like ours? Are there potentially habitable planets? PLATO's photometric precision and mode of observation will help determine the frequency of Earth-like planets. New insights into the formation and evolution of planets and planetary systems, as well as the evolution of stars, is also anticipated. The PLATO mission involves launching a satellite platform and a high-tech payload into Earth's orbit, where it will operate from the Lagrange point 2, 1.5 million kilometers away from Earth. The planned mission duration is 4 years, but if everything goes according to plan, this will be extended another 4 years. PLATO's launch mass is around 2,500 kilograms, 533 kilograms of which are the satellite itself. It will be launched on the Ariane 6 rocket. The Ariane 6 rocket is an expendable medium-lift launch vehicle which costs around $118 million per launch. The PLATO mission will launch from the Guyana Space Center, Ensemble de Lancement Ariane 4, or ELA-4. The Guyana Space Center is also known as Europe's spaceport. Located northwest of Kourou in French Guiana, 500 kilometers north of the equator. There are specific benefits to launching at the equator. Most notably, it increases the fuel efficiency as the rocket can gain an extra velocity boost of roughly 1,600 kilometers per hour from Earth's eastward rotation. PLATO was first proposed in 2007 to the European Space Agency. The European Space Agency selected PLATO as the third medium-class mission in February 2014. It was then officially adopted into the science program on the 20th of June 2017. This was a key milestone as it allowed the mission to progress from being just blueprints into the actual construction phase. The European Space Agency's PLATO mission is due to launch in January 2027. The PLATO spacecraft is a sophisticated 3-axis stabilized observatory designed for extreme precision. With a launch mass of approximately 2,500 kilograms and a deployed wingspan of 9 meters, it is roughly the size of a small van with wings, engineered to protect its delicate sensors from the harsh environment of space. To ensure maximum scientific performance, the spacecraft uses a modular design that separates sensitive optics from noisy housekeeping systems. The payload module houses 26 cameras on a rigid optical bench. To maintain perfect alignment, the structure is primarily made of carbon fiber to minimize thermal expansion. It is mechanically decoupled from the rest of the ship using a specialized truss structure with flex joints. The service module provides the infrastructure for the mission, including propulsion, power, and communication. It serves as the stiff base for the payload and the primary interface with the Ariane 6 launcher. The service module manages several critical subsystems to keep the mission running for its 4 to 8 year lifespan. A massive sunshield protects the cameras from solar radiation while doubling as a mount for solar panels. These panels provide the 3,000 watts of power required to operate the 26 cameras and onboard computers. To detect the tiny dip of an Earth-like planet, the spacecraft must remain incredibly still. This is managed by an attitude control system featuring reaction wheels, gyros, and star trackers. The cameras must stay cold and stable. The spacecraft uses a combination of heaters, radiators, and multi-layer insulation to maintain a radiative cooling environment, even while electronics on the bottom panels generate heat. PLATO is a data-heavy mission, generating roughly 435 gigabytes of data per day. To handle this, it uses a steerable dual XK band high-gain antenna. While X-band is used for basic satellite control, the K-band transmits science data to Earth at rates of up to 72 megabytes per second. The name PLATO, PLANetary Transits and Oscillations of Stars, perfectly describes its two-pronged approach. It doesn't just find planets, it studies the stars they orbit to understand the planets themselves. To understand a planet's nature, we need 3 pieces of a puzzle: radius, how big it is; mass, how heavy it is; and age, how old it is. PLATO is the first mission to target a benchmark of 3% radius accuracy and 10% mass accuracy for Earth-sized planets around Sun-like stars. Without this precision, a planet could be a giant rock or super-Earth, or a tiny ball of gas, a mini Neptune. With it, scientists can determine if a planet has a massive iron core like Mercury or a deep ocean. We are currently limited by a sample size of 1, our own solar system. PLATO will observe systems at various life stages to see how they evolve. It will help determine when molten magma oceans on young planets solidify into crusts. By measuring coplanarity, which is whether planets orbit in the same flat plane, and eccentricity, how circular the orbits are, PLATO will reveal if the layout of our solar system is normal or a cosmic fluke. The oscillations part of PLATO refers to astroseismology. Stars vibrate due to internal convection, creating starquakes that send sound waves through their interiors. By listening to these vibrations, PLATO can see inside a star, much like an ultrasound. This is the only way to get a precise age for a star and its planets. PLATO will investigate if a star's metallicity, or its chemical makeup, determines what its planets are made of. For example, do stars with more iron produce planets with bigger iron cores? One of the most startling discoveries by the Kepler mission was that planets don't come in every size. There is a valley, or a gap, in the population. There are many planets smaller than 1.5 times Earth's radius, so super-Earths, and many larger than 2 Earth's radius, sub-Neptunes, but almost none in between. The theory is that scientists believe this is caused by photoevaporation, where the intense radiation from a star literally blows the atmosphere off a planet, shrinking it from a sub-Neptune down to a rocky super-Earth. Currently, we only see this valley in planets very close to their stars. PLATO will look further out to see if this atmosphere stripping happens in cooler, more distant orbits. To date, our map of the galaxy is highly skewed. Missions like TESS are great at finding planets around M dwarfs, which are small, dim red stars, because those planets are easier to see. However, M dwarfs are prone to violent flares that are likely to strip away life-supporting atmospheres. The 1 astral unit gap. An astral unit is the distance between the Earth and the Sun. We currently have almost zero data on Earth-sized planets at 1 astral unit around Sun-like stars. This area of our scientific charts is effectively terra incognita. PLATO is specifically designed to stay pointed at the same star for years. This long-duration stare is the only way to catch the tiny, rare transit of a planet that takes a full year to orbit its star. PLATO will also explore the ice line, which is the boundary in a solar system where it is cold enough for water, ammonia, and methane to freeze into solid ice. Most gas giants, like Jupiter, are thought to form beyond the ice line. By studying planets in these cold, distant orbits with periods over 100 days, PLATO will complete our understanding of how entire planetary systems are born from the original disk of dust and gas. PLATO will act as a scout for other flagship telescopes. It will identify Rosetta Stone planets, worlds orbiting stars so bright that the James Webb Space Telescope or the future Ariel mission can sniff their atmosphere. These follow-up missions will look for water vapor, carbon dioxide, or even oxygen. By combining PLATO's data, so mass, radius, and age, with the James Webb Space Telescope's data on atmosphere, we will finally have a complete 3D profile of another world. PLATO represents the transition from the era of just finding planets to the era of truly understanding worlds. It is the bridge that will finally allow us to compare our home directly to the rest of the galaxy. The most profound question in modern astronomy is, how common are worlds like ours? While we have discovered over 5,500 exoplanets to date, we still do not have a clear answer. This is because current technology is biased. It is very good at finding large, hot Jupiters or planets that orbit very close to dim red dwarf stars. The frequency of Earth-sized planets orbiting Sun-like stars in the habitable zone is a value scientists call Eta-Earth. Currently, our estimates for Eta-Earths are wide-ranging and uncertain. Some models suggest only 2% of Sun-like stars have an Earth twin, while others optimistically suggest 100%. PLATO's primary scientific legacy will be its ability to replace these theoretical guesses with precise observed statistics. By the end of its mission, we will finally know if our solar system is a cosmic rarity or a common standard. PLATO is not just looking for a planet. It is conducting a massive census of the solar neighborhood. To do this, it categorizes its targets into specific samples. The bright samples, P1 and P2. PLATO will monitor over 15,000 bright, sun-like stars with extreme precision. Because these stars are so bright, they allow for high-fidelity science. When a planet is found here, we won't just know it exists. We will be able to determine its mass, radius, and age with unprecedented accuracy. The statistical sample, P5. Beyond the VIP bright stars, PLATO will observe at least 245,000 fainter stars. While we may not be able to measure the individual masses of all these planets, this sample provides the big data necessary to understand the architecture of the Milky Way. It will help us understand the radius valley, the mysterious gap in planet sizes that suggests some planets lose their atmospheres while others keep them. The Holy Grail of PLATO is the detection of small rocky planets with a radius of less than 2 times that of Earth within the habitable zone of G-type stars, which are stars like our Sun. To confirm a planet is truly Earth-like, we need a radius accuracy of 3% and a mass accuracy of 10%. PLATO is a first mission designed to specifically meet these tight requirements for Earth-Sun analogues. Depending on the actual frequency of these planets, PLATO is expected to identify between 6 and 280 solid candidates. Current simulations suggest a likely sweet spot of 50 characterized habitable zone planets. You might wonder why we need PLATO if we already have the Transiting Exoplanet Survey Satellite, or TESS, mission. While TESS is a brilliant scout, it has limitations that PLATO is designed to overcome. TESS generally scans a patch of sky for 27 days. This is great for finding planets with 5-day orbits, but finding a planet with a 365-day orbit like Earth, you need to watch for years. PLATO will stare at the same patch of sky for at least 2 years at a time. TESS focuses heavily on M dwarfs, the small, cool red stars, but PLATO focuses on F, G, and K stars, which are more stable and similar to our Sun. PLATO's unique 26-camera design gives it a massive effective aperture, allowing it to see the tiny 0.01% dip in light caused by an Earth-sized planet, a signal that is often lost in the noise of other telescopes. A planet is only as well understood as its host star. PLATO uses a technique called astroseismology to study the internal structure of stars. By measuring starquakes, the vibrations in the star's light, PLATO can determine the star's mass, radius, and age. Knowing the age of a planetary system is a game changer. It allows us to study how atmospheres evolve and whether a planet has had enough time for life to potentially develop. PLATO will provide the age of its host stars to within 10%, something never before achieved on such a large scale. The mission doesn't end in space. Once PLATO identifies a candidate, it triggers the Ground-Based Observation Program. This is a global network of the world's most powerful telescopes, such as Espresso, or the Very Large Telescope in Chile. These ground-based instruments measure the radial velocity, the tiny wobble of the star, to confirm the planet's mass. This synergy between space-based transit data and ground-based wobble data is what allows us to calculate the density of the planet and determine if it is made of iron, rock, water, or gas. PLATO is more than just a telescope. It is a foundation for the next century of astrobiology. It will provide a treasure map of the best nearby worlds. These planets will be the primary targets for future flagship missions like the James Webb Space Telescope and the upcoming Habitable Worlds Observatory, which will scan their atmospheres for biosignatures. the chemical fingerprints of life. By 2030, thanks to Plato, we may finally be able to point to a star in the night sky and say, there is a rocky planet there, the same age as Earth, with the right conditions for life. Plato's massive dataset allows scientists to move from looking at individual worlds to understanding the global recipes that create entire planetary systems. By observing thousands of systems at various ages, the mission serves as a laboratory for testing how planets are born and how they die. Astronomers use complex population synthesis models to simulate the first 100 million years of a solar system. Plato will provide the data needed to refine these models into 3 key areas. Scientists debate whether planets grow by sweeping up tiny pebbles or by colliding with massive planetesimals. Plato's precision helps determine which process is more common. We know planets don't always stay where they were born. Interactions with a gas disk can push them inwards towards a star or outwards. Plato will map where planets of different sizes end up, revealing the history of their travels. By finding planets with high water content, Plato helps us understand how water, the essential ingredient for life, is distributed throughout a system, and whether Earth's oceans were a rare accident or a standard outcome. Because Plato can determine the exact age of a star, it can track how systems change over billions of years. Plato will track atmospheric erosion. Just as Mars lost its atmosphere due to solar wind, many exoplanets are slowly being stripped by their stars. Plato will allow us to see this process at various stages. Plato will also look for exotic environments. It will search for Tatooine-like worlds, circumbinary planets that orbit 2 stars. These extreme environments act as stress tests for our theories of gravity and planet formation. While planet hunting is the core science, the Plato Complementary Science program opens the telescope data to the entire astronomical community. A year before launch, PLATO CS will release a massive treasure map classifying the light behavior of stars in its target field using machine learning tools. This database will identify variable stars, which are stars that pulsate or flicker, binary systems, which is a pair of stars orbiting each other, and target of opportunity. These are rare events like novae or supernovae that require immediate attention. While the main mission studies sun-like stars, PLATO CS targets massive stars 1.3 to 9 times the mass of our Sun using gravity modes. Gravity modes travel deep into the star's core. They allow us to measure how fast the core rotates and how chemicals mix in the engine room of the star. This data acts as a biological clock for massive stars, helping us predict when they might eventually explode as supernovae. Plato isn't just looking at the solar neighborhood. It's looking at the history of the Milky Way itself. By observing red giants, stars in their twilight years, Plato can act as a galactic archaeologist. Red giants are excellent traces of galactic history. Plato can date these stars with 10% precision, helping us reconstruct how our galaxy grew and changed over 10 billion years. By studying mixed modes, a combination of pressure mode and gravity mode, astronomers can see how the cores of stars speed up as they age, providing a deep look into stellar physics. Plato is uniquely suited to watch high-energy transient events in compact binaries, systems where a star is being eaten by a white dwarf, neutron star, or a black hole. PLATO can track super outbursts and super humps in real time. These are massive explosions caused by instabilities in the disk of material swirling around a dead star. Using its specialized fast cameras, PLATO can provide multicolor data, red and blue, during an explosion. This allows scientists to map temperature changes and energy flows during some of the most violent events in the universe. While PLATO's primary goal is to find another Earth, its secondary legacy will be a revolutionary new understanding of how stars live, how galaxies form, and how the most extreme objects in the universe behave. To maximize its scientific return, PLATO categorizes its millions of potential targets into 4 distinct samples. These samples are defined by the brightness of the star and the scientific precision required. PLATO doesn't just look at everything the same way. It organizes stars into groups to get the best results. The VIP stars, P1 and P2, these are the 15,000 brightest stars similar to our Sun. PLATO watches them every 25 seconds to find 100 plus Earth-like planets with extreme precision. The cool neighbors, P4. This group focuses on 5,000 red dwarf stars. Since these are the most common in the galaxy, PLATO wants to see if they form planets differently than our Sun does. The Big Data Group, P5. This is a massive census of 245,000 stars. PLATO checks in on these every 10 minutes to create a giant map of how many planets exist across the whole Milky Way. Because PLATO takes so many pictures, it can't send them all back to Earth at once. It uses 2 methods to save space on its hard drive. The first method, for the VIP stars, PLATO sends back a tiny raw cutout of the pixels around the stars. This is the highest quality data possible. The second method, for the Big Data Group, the satellite's computer does the math on board. It just sends back a simple graph of the star's brightness over time, which takes up much less room. PLATO is a wide-eye observatory. Its field of view is 20 times larger than Kepler's. PLATO will point at one part of the sky for 2 whole years. This is long enough to see an Earth-like planet complete a full trip around its star. Every 3 months, the satellite does a ballet move rotating 90 degrees to make sure its solar panels stay pointed at the sun while its cameras stay locked on the same stars. Before a discovery is announced, the data goes through 5 levels of cleaning. Raw pixels are turned into clean graphs, removing any shaking from the satellite. Scientists find the first hints of a planet and calculate how old the stars are. Ground-based telescopes on Earth step in to weigh the planets. The gold standard catalogue is released, listing fully confirmed and understood worlds. PLATO has a tag-team relationship with the world's biggest telescopes on the ground, like the VLT, or Very Large Telescope, in Chile. By watching the shadow of a planet, PLATO can tell us how big it is. By measuring the star's tiny wobble, as slow as a human crawl, ground telescopes can tell us how massive the planet is. The result equals density. This tells us if the planet is a giant rock, a water world, or a ball of gas. PLATO isn't just for the mission team. 8% of its time is open to the public for bonus science. This can include supernovae, which is watching stars explode in distant galaxies, binary stars, studying two stars that dance around each other and space emergencies. If something rare and exciting happens suddenly, like a nearby star exploding, PLATO can hijack its own schedule to watch it happen. PLATO is photon noise limited. Now this means its cameras are so good that the only thing limiting the image quality is the physical amount of light coming from the star itself. Engineers have planned for a worst-case scenario where 2 of the 24 normal cameras might break during the mission. So even if this happens, the mission will still meet 100% of its goals. Previous telescopes, like Kepler, looked at dim, distant stars. PLATO looks at bright, nearby stars. This ensures that once we find a planet, the star is bright enough for us to study the planet's atmosphere and search for signs of life. For centuries, we've looked at the stars and wondered if we are alone. By 2031, PLATO won't just be giving us coordinates on a map. It will be giving us a new perspective on our place in the universe. We are about to find out if Earth is a cosmic rarity, or if the galaxy is teeming with worlds just like ours. The search for Home 2.0 has officially begun.